Hi and welcome to lecture 8.1 of the Domain-Specific Languages of Mathematics course. I will continue on from the linear algebra lectures from last week and go towards the definition of the Laplace transform. But let's start with an example of a vector space. So this example is an infinite dimensional vector space. So we can't really have a finite collection of base vectors, not even a countable collection, because here I've got functions from real to real. So this being the vector space means that each function, whatever function from real to real, is an element, is a vector. So sine is a vector, const 1 is a vector, exponential function is a vector, identity function is a vector. So these are all elements of the vector space. And then we can start talking about transformations between vector spaces. So here is one. So we have talked a lot this course about the derivative operator. So the derivative takes a real-to-real function and returns a real-to-real function. So it can be seen as a function between two vector spaces, the R2R and R2R. And the question is here, is this a linear transformation? So I defined a predicate linear transformation earlier, and let's see what that would mean for the vectors for D. So first, let's write it out. So what should hold for this to be a linear transformation? Well, there are three operators. D should be an H0 from the zero of the vector space. So I'll write a 0 with little f for functions, and it should return the 0 of the same vector space V. So if we expand this, well, let's take the overview first. So H0, it should also be the same D, should also be H2 from plus for functions to plus for functions. And same with negation. So the derivative operator, to be a linear transformation, it needs to satisfy all of these three operations. So that's called unary minus for neg, for negate. Okay, so all of these three things should hold. And so there's an and in between here, this and this and this. If that's true, then yes, D is a linear transformation. So let's try to write it out and check if we think it's satisfied. So if you remember the definition of an H0 predicate, that's very simple. It says, so this is, if you expand it, it says that D applied to 0f should be equal to 0f. So the operator should take the unit in this, the additive unit here to the additive unit there. So what is 0f? Well, 0f is actually the constant function. So the question is, I can write it next up here. This is const 0, where this other 0 is the 0 in reals. And well, this is the same const 0. So what is the derivative of the function const 0? Well, the derivative of all constant functions is const 0, so this definitely holds. So we can say here, green, yes. This first part holds. D preserves zeros. Okay, next question is, what is this? So let's write out the definition of this predicate. So this is the same as for all f and g of type V, that is functions from R to R. If we apply D after addition, we should get the same result as if we apply D before addition. And then we have to remind ourselves What does it mean to add functions? Well, it just means pointwise addition. So the function f plus g is the function which at each point x returns f of x plus g of x. And we know that derivative is linear. We've proven it when we talked about the definition of derivative in terms of the limits. So derivative of f plus derivative of g as functions is actually proven to be equal to this one earlier. So the same yes holds here as well. Maybe I should make a little green arrow. So 2 yeses so far. And I see here that I made a mistake in the typing of the last one. It is an age 1, not an age 2, because negation, unary minus, has one argument. So if we write that one out, this is equivalent to, for all f of type v, the derivative of the negation of f should be the same as the negation of the derivative of f. And if we think of this in terms of scaling with minus 1, we know that the derivative is homomorphism with respect to scaling. So this one also holds. So we actually have 3 yeses here. All these 3 requirements are satisfied, which means that yes, D is a linear transformation from functions to functions. That means also if we had a basis here, we would be able to write a matrix describing this transformation. But it's difficult when the vector space has so many dimensions. Fortunately, we know how to define derivatives anyway. Okay, and I think this was basically the same thing I had pre-written to make sure it fits. Let's now look at some examples. So remember I said that v had as vectors all normal functions from R to R. So the normal exponential function is one element. So you may get confused here and think, well, exponential function, that's not very linear. But there is no requirement that the elements of the vector space be in any sense linear. If you think about the normal vectors, say 3-dimensional vectors, the 3 components don't have to be linear in the index 1, 2, 3. You can fill in whatever numbers you want there. And similarly here, the exponential function is a vector in the sense that at each index, at each input value, it has a particular output value. And there is no requirement that these output values be related in any way to each other. Only that they are uniquely determined by the index. Okay, so this means that we can apply, for example, the derivative, and we know what happens if you apply the linear transformation d to exp. We know that exp is one of these functions which has itself as its derivative. This also, by the way, means that exp is an eigenvector for the transformation d here. It's something where if you apply the transformation, you get back a scaled copy of itself. In this case, it's scaled by a factor of 1. Okay, so then let's look at a slightly more general example, which we will have use of a few slides further on. So here I've defined a family of vectors. So notice that there is a little index s here. S is of type real. So for each real number, I define a vector gs. And what is the type of gs? Well, let's be back again. So gs is of type real to real. So gs is a vector. I mean, this type is the same as v. So gs applied to t is defined as the exponential function of minus x times t, which means that they are different. For example, g minus 1 is the exp we had here, because minus 1 is 1, so that would be just exp t. So I define it as a function, but notice that gs is the vector here. Okay, as it's a vector, we can ask ourselves, what do we get if we apply d to this vector, gs? Well, we should get a function, because it should get a vector out. So this function then, in turn, will take a t as an argument. And then let's see. So we should compute here the derivative of this expression with respect to t. And we know one of the rules for derivatives is you can take, when you have a composed function of exp and an inner function, you can compute the derivative of the external one, multiply the result by the derivative of the internal one. In our case, that means we will still have exp of minus s times t, but we will also have to multiply with the derivative of the inner function. And the inner function is just a scaling by minus s. So a linear function, lambda t to minus s times t. The derivative of that is multiplication by minus s. Okay, so if we simplify this slightly, on the next line we can say this is minus s times, well, actually, minus s times what? If we look here what we've got, this first part is the same as we had before. So it's actually minus s times gs. Of t. Okay, so we have sort of multiplied our original function, or the return value of our original function, by minus s. And if we now step out one step and say, okay, this means that d of gs, which is then lambda t to minus s times gs of t, that can also be written as a scaling of the vector gs. So this is equal to scale for the function vector space by minus s of gs. So we can just check perhaps, or remind ourselves what the definition of scaling is for function. So scale f takes, in this case, a real number, a function in the vector space, and it returns a function, and scale f of c f is equal to the function that multiplies f of t by c. And if you want to match, you can see that gs here is the f and minus s is the c. So the derivative of gs is a vector pointing in the same, or actually the opposite direction of gs, and it's scaled by this factor. So this is actually also an eigenvector. gs is something which is returned by this operation scaled by a constant. In this case, minus s is the constant. We'll also use that later. Yeah, and this was just what I already written, pre-made. Okay, so one more thing. We need to prepare ourselves for some computation later, and you've seen in lots of cases we've used what the derivative of a function is and what its value is at 0. So let's see, what is the value of gs at 0? So this is just exp of minus s times 0, which is exp of 0, which is 1. So taking at 0, all the gs functions for every s is just 1. And then the s determines how quickly they decay from 1. I mean, actually, I can make a very little small sketch here. If we have the t-axis going away in this direction, and then we have, say, 1 here. So we know that all of the GS start at 1. And then let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. If S is 1, then this should decay to 1 over E, which is somewhere between half and a third. So somewhere here. So let's see if I can draw a curve which looks reasonably like an exponential function. So this function here is probably G1. And what happens if I increase the index to G, if we say G2? Well, then it decays quicker. It decays twice as fast. So that means that G2, let's try to draw that with another color. Oops. Now I'm pressing strange buttons here. I'm trying to draw a curve which shrinks twice as fast. So this is an approximation then of G2. And then you can also realize that if you get a high index of G, it will go down to 0 very quickly. And then if you get a very small index, it will decay very slowly. So maybe we can draw a little yellow one here, which goes away quite a long way, and let's say that's G4, G 0.2, for example. And G0 would mean a function which is just constantly 1. Okay, so that was one of the components, understanding a little bit of this family of functions G. So they have the property that if you apply derivative to them, they just return a scaled copy of themselves. And this is roughly what they look like. And we've computed now that d of x is x, d of gs is scale minus s of gs. And another operation we can remember from earlier is if we take the derivative of a multiplication of two functions. So multiplication of functions here means point-wise multiplication. So the function which at every point is the product of f and g. That's derivative of the first component times g plus f times derivative of the second component. So this is one of the equations we will also have use for later. This is not something we can do in general for a vector space. We don't usually have multiplication defined. So this is not an operation we usually have, but this is just an operation on functions, which we can reuse here. Okay, now let's look at the opposite of derivative, the integral. And I've said up here, let's look at integral as a linear transformation. So here I've chosen to ignore the first argument to the integral that we used a lot in week 6, the putting in the sort of value at 0. So here I just say, okay, the value at 0 is 0 to simplify matters, to see the symmetry here. So this I is a special integral from 0. It has the same type as D. So it goes from a vector space of functions to a vector space of functions, just as D. And how do I define it? Well, I of an f at the point x is the integral from 0 to x of that function f. Or in more traditional math notation, the integral from 0 to x of f of t dt. So the area under the curve. And if f is to be already the derivative, then we can compute here the integral of the derivative of f at x is the integral from 0 to x of f prime of t dt. And if you remember the rules or the notation for integrals, if you have something that you want to integrate, then you use these brackets and the upper and ending limit, and you put the integral, the indefinite integral here, which is for f prime, the integral is f expression. And then you insert x for t and 0 for t with the subtraction. So the top end minus the lower end. So this is the value of I of d of f. So it basically returns f of x. The only difference is this f of 0. And that's always the case. You remember, when I throw away the information in d of f, I will not anymore know what happened at 0. I will only know what changes happened after 0. Okay. And if we now want to do this for the special case of f times g, then not surprisingly, if we insert f times g here, we get f times g at x and f times g at 0. And maybe you're a bit unused to this notation. This is the same as f of 0 times g. Oh, sorry, I should erase that. F of x times g of x. Then here it's also f of 0 times g of 0. Or, I mean, if you really want it in the classical math notation, f of x g of x minus f of 0 g of 0. But I'm just typing it out so that one recognizes it for future use. Yeah, and this was exactly what I was writing before. Oh, no, sorry, yes. I've just repeated what I wrote before up to this point, but then I want to use this equation. I'm saying, oh, by the way, the derivative of f times g, we know another expression for that. So here I use the expression for derivative and use that to compute it. Here I'm using the right-hand side to compute it. So I've taken this first step and jumped over here. So then it says the integral of this first term plus the integral of this second term. And why have I moved out plus here? Well, because we know that the integral is linear. So now I have an expression which relates the integral of, well, I mean, if I integrate the derivative, that's like the inverse operation, but then I also get this. So we get an equation here between two expressions involving derivative, which I make use of in the next step, and it's all being equal to this simpler expression, which doesn't involve any derivative or any integration. So this is basically the formula for integration by part, if you're wondering where I'm heading. Okay, now I've sort of repeated that up here. That was the end of the previous slide. That f times g at x minus f times g at 0 is the same as the integral of these sort of interesting looking expressions. And now I want to use this for two special functions, f and g. So f is arbitrary, but for g I use the gs we defined. Remember, that was the function returning e to the power of minus st. And we remember that the derivative of this was just a scaling of the same function. And now we want to restrict ourselves, because otherwise the computation won't get through, to functions f, which satisfies this property. So the property says that when x goes to infinity, f scaled by gs should go to 0. So that means, for example, I mean, if this s is 1, then this is e to the power of minus t, which means that this function is not allowed to grow faster than e to the power of t, because if it would, or it not as fast as even. So it has to be reasonably sort of small. But small here could mean things like x to the power, or t to the power of 5. That's killed by the exponential factor. So f can be quite lots of functions, but they can't be too big exponential. Okay, but given this requirement, then I can say that when I will let this expression here, I will let x go to infinity. That's what I'm doing when I'm moving down here. So then f times gs, that will go to 0. So this first expression becomes 0. So I'm rewriting the equation up here again with this special choice of f, g, and letting x approach infinity. So then I get 0 minus this computation. And then over here, I've just written the same expression with GS, and I use the symbol infinity here. So the symbol infinity here is then a shorthand notation for the limit of the expression with x as x goes to infinity. But I use it here because I will move back to another expression later. And then here I've just computed the derivative to be the scaling of GS. Otherwise it's the integral, it's the same, it has f multiplied in the same way and applied to x, which is approaching infinity. Okay, now I can simplify this a little further. So 0, so I will rewrite this equation. So this is equivalent to 0 disappears, I get, and yes, 0 disappears and GS of 0 we computed, that's always 1. This is actually just minus f of 0. And then on the right hand side, I still have this integral expression. Integral of df composed gs at infinity. But for the last expression, I will simplify it a bit. So this may not be obvious, but when I scale this vector and then multiply by anything, it's the same as scaling. So I should take that in 2 steps. So let's say this part here, this internal part, that's the same as moving the scaling out 1 level. Scale of minus s of f times gs. And not only that, the integral is linear. So if I do a scaling inside the integral sign, I can also move it out. And moving it out here means that instead of plus I will get minus s times I. And then what's left inside is just f times gs at infinity. So I've step by step sort of from this one go into infinity, specialize g to this particular function, and we've got an equation here, well, relating some expressions which we will have good use for later. And the key thing to notice here, why we've done this and why we set it up, is because we have got gs in 2 places. So before we had a derivative of gs, but as we could compute it, we got rid of a derivative. So we've got the same function gs in 2 places, and we're relating some integral of the derivative of f to the integral of the function f. And that is the key to the Laplace transform. Okay, so now I will introduce a name for a certain pattern here. So the pattern, if I underline it, oops, there's an infinity missing, so I'll have to move this slightly to the right. I was a little quick in copying. The integral to infinity there. Okay, so the pattern I'm noticing, I'm integrating a function to infinity. And not only am I integrating a function to infinity, I'm integrating a function multiplied by gs to infinity. So let's define a name for that. So let's up over here in a corner, let's define L of, well, some function, let's call it, use the pattern here for the second occurrence, LF, yeah, actually just L of f. So the pattern that I've identified is this pattern. So the integration of f times gs up to infinity. So L of f at a certain point s, there is also, because we have to know which g it is, So L of f at a certain point s is defined to be the integral of f times gs to infinity, which, as we remember before, is just the integral from 0 to infinity of f times gs. So if we define this to be L, so notice what L is doing. It's taking a function as one argument and s as another argument. Then we can notice that this is the same pattern. The only thing changed from here to there is that we have derivative of f instead. So if we write up this equation once more, we say it's minus f of 0 equals Laplace of the derivative of f at s minus s times Laplace of f at s. So I've reused this pattern LFS twice, once with just f as it was defined and once with derivative of f. And the last step one usually does is to put this on the left-hand side instead of the right-hand side. So let's extract this expression. So computing the Laplace transform of the derivative of a function at s, meaning that we're using the gs, the function with the index s there, that is the same as, and if we look here, it's minus f of 0, and then as we move this over to the other side, it's plus s times the Laplace transform of f and s. And this may now look rather abstract, and it is rather abstract, but the key here is that we've applied a transform to a derivative, and we got out an expression without the derivative. Instead of derivative, we multiplied by s and subtracted f of 0. So this means that we can use this to get rid of derivatives in equations. So if we have an ordinary differential equation and we use the Laplace transform on it, we will get an expression without derivatives, but with just multiplications. So something which looks like a polynomial expression, a polynomial equation at least. Okay, and I think here I've just, I wrote that beforehand. Oh, yes, I should mention also this s here, which we talked about before. S doesn't need to be a real number. So often this typing is what's used, that the function f is a real function, but the s argument is a complex valued value. And that means that, well, the exponential is also defined for complex numbers, but the whole integral here will also be a complex number. And that means that actually the type of L, let's try to fit that in as well, L takes a function from R to R and returns a function from C to C. You see here, L of f is a function which takes s to this one. Okay, to sum up here, we've defined the operator L that takes a function and then at a certain point s, which can be a complex number, it integrates the product of f and gs. Remember, g is a family of functions. For each s there is one function. It's just, as we've written here, the exponential of minus s times t. And this will work if we assume that the function f is not too big, so it will be killed by this exponential decaying function as x goes to infinity. And it's also worth noting that the s used inside here is not involved in the integral. The integral is in the variable t, which is used, so f does not depend on s, and t does not depend on s. It's only the factor in front of t, so the speed at which we're decaying in the exponential function here, that is what is affected by s. And the formula we found out was that we can Laplace transform a derivative, and we can get an expression which involves the Laplace transform still, but not any derivative. And in total, the function L goes from v to w. We know that both v and w are vector spaces. And what we haven't shown here, but which is a good exercise, is to show that actually L is a linear transformation from v to w. Meaning that it preserves the zero of this one and goes to the zero in w. It preserves addition to the addition in w, and it preserves scaling in v. It becomes scaling in w. And that's a good exercise in just the properties of integrals. And the key here is that the integral itself is linear. Okay, this was all for this part. We'll continue with using the Laplace transform later. And I should mention that in the book, the Laplace transform is derived in another way. And the purpose of doing it differently here is to make sure that if you find one confusing, then maybe the other one helps, and the opposite. And in general, it's good to see something explained in two different ways. It's like seeing the same shape from two different directions, and you get more depth in your view in that way. Okay, thanks for this part.